Hey everyone, welcome to our next video. Excuse me. Our video today is starting on 4.3. If I could scroll down, there we go. 4.3, which is logarithmic functions. And applications. Now, we won't do too much in the application sense because usually we cover that in another course. So if you have to go to Math 125, we do a lot of applications of logarithmic functions. And then if you go into the calc series, you're going to do, well, you're going to use logarithmic stuff in other things, but you'll also see applications. So we're mostly just kind of doing the main parts. So our first thing is that log functions, or logarithmic functions, but we usually just say log, are of the form y equals log base A of x. Now in this case, A is the base, just like it was with exponential functions. We called A the base. We're still calling A the base here. Now this is equivalent to the exponential function A to the power of y is equal to x. You'll notice I'm not writing that as y equals. It's because the exponential and the logarithm are inverses of each other. So it's like that x and y has been switched around a bit. Another really important thing about logarithms is that the inside of the parentheses has to be greater than 0. So we are going to have domain restrictions here. It also means that we're going to have a vertical asymptote. Also going to have a vertical asymptote when graphing. And we'll see that later, and first we're just kind of going to talk about the logs a little bit, do a little bit of evaluation problems and stuff like that. So I want to explain something about logs first. If I say 2 cubed equals 8, in a log function, the way this would look is we would say the log of the base 2 of 8 is equal to 3. Pretty much what you're saying here is that the exponent you would put on 2 for it to become 8 would be 3. So something you'll hear me say a lot is that logs are equal to exponents. Logs are equal to exponents. So when you say, for instance, log base 3 of 9, what I'm asking you is what exponent would you put on that base of 3 so that it becomes 9? So that's what logs are asking. They're saying, what exponent do you put on the base for it to equal the parentheses? And in this case, that would be 2. So we want to make sure that we understand the relationship of logs, and then that makes it easier to go to the exponential form, because then if I say, okay, move this to exponential form, well, the exponent I'd put on 3 so that it equals 9 is 2. So that's in exponential form. I think it's a lot better to understand the actual relationship of logs with exponentials than to just remember a process and, oh, this goes here, this goes here. You'll get confused that way. Now we do have something called the common log. And so this is just some notation stuff. So if you ever see something that says f of x equals log and it just doesn't have a base written there, that base is understood as 10. So this is equal to log base 10 of x. So I say that that's understood. It's kind of like whenever we write, like we always say, oh, there's this invisible 1 in front of a variable if it doesn't have a coefficient in front of it. It's just something that is understood. So if you don't see a base on log, then that base is automatically 10. The other common notation that we're going to see is for the natural log. And the natural log is written as ln of x. But what it really is it's just the regular log, but it has a base of e. So it gets this special notation where we write it as ln. Sometimes you'll see me as write it as ln, and then I'll put the little e at the bottom. Now the natural log ln is very special that it has e. You would really never see this. Like that's definition what it is, but you would never actually write that. Log is for 10 or any other like weird base. So if we ever use like 2, 4, 80, we're going to write log. ln is specifically used for e. So I think first I just want to practice us finding some log values, just practicing evaluating logs. So example 1, I'm going to say evaluate the following. And I'm just going to write a bunch of these on here. So you can go ahead and pause and take a minute to write these down, but I'm going to go ahead and get started explaining them. So if we start off with log base 3 of 9, what this is asking is what exponent do you put on 3 so that it equals 9? In this case, it would be 2. So this equals 2. Now you can actually show a little bit more work than this. Sometimes I see students maybe like to say, oh, it's equal to x, and we're trying to find what it equals. So they like to write it as an exponential. So this would be 3 to the power of x equals 9. So x would equal 2. You can even show more work than this and use the properties that I showed you last time in the last video and write that 9 as 3 squared, and then again you get x equals 2. However you like to do it is fine. I really just need that final answer. Sometimes we will need to show more work, and sometimes maybe we don't. For part B, we're looking for, first we need to decide what our base is because the base isn't written. So since there isn't one, it's just 10, since it's log. And so we're being asked, what exponent do you put on 10 for it to equal 1,000? In exponential form, we're asking 10 to the what equals 1,000. So in this case, that would be 3. 10 cubed is equal to 1,000. For my next one, again, I don't have a base written. Since it's ln, I know that my base is e. So I'm being asked, what exponent do you put on e so that it becomes 1? You know, as I'm going through this, I'm not sure that I defined e for you in the exponential section. I'm looking back. No, I didn't. Okay, I'm sorry about this. I'm going to talk about it now, but it's a little late for me to be talking about it. E is just a number. I kind of just started going through it, but E is a number kind of like pi, where pi goes on forever and ever and ever, so we just call it pi. E is the same thing. It goes on forever and ever and ever, so we just called it E. But it's a really common base to see. It's used in a lot of application problems. E is like 2.718, and that's all I know. I don't know any more of the numbers, but it's something like that, but it goes on forever and ever and ever. And it's just something really common that we see in exponential and logarithmic problems. So I apologize for not explaining that. It's not necessarily a variable, it is a number, kind of like pi. So what exponent would we have to put on something so that it becomes 1? And this one would be 0. Anything to the power of 0 equals 1. So that one might have been a little tricky. Part D, so I'm being asked, what exponent would you put on a half so that it becomes 8? And in this case, that would be -3. If you'd like me to show some work, I can. So 2 to the negative x, I can rewrite that. And then 8 would be 2 cubed. So I get -x equals 3. So x equals -3. The negative is what flips me so that I'm no longer a fraction. And then I got to get that 2 to become 8. So that's where the 3 comes in. My next one, I'm being asked, what exponent would you put on 4 so that it equals 1 over 64? So it definitely needs to be negative. And then 4 cubed is 64. So this one is also equal to -3. For f, my base is not written, but because it's ln, I know that the base is e. So I'm asking, what exponent would you put on e so that it becomes e to the 4th? And so in this case, see how our bases are the same? Well, it's just x equals 4. So this equals 4. What exponent do you put on e for it to be e to the 4th? 4. Now my last one is a little bit trickier. So I'm being asked, what exponent do I put on 4 so that it equals 32? The issue is that 4, like there is no power, like a whole number at least, that you could use to get to 32. However, these do have the same base. So 4 can be written as 2 squared, and 32 can be written as 2 to the 5th. And so I'm using that property from last time, where if your bases are the same, you can look at the exponents. So this would be 2x equals 5. So x equals 5 over 2. So this equals 5 over 2. We'll actually do more like that a bit later, but it's something that I felt I could introduce now. Now that we've seen some log evaluation problems, I do want to practice just some moving from exponential form to logarithmic form and vice versa. So I'm going to say rewrite each log equation as an exponential and vice versa. I've got a few of these. Log base 5 of 625 equals 4. B, let's do log base 3n equals 5. C, we'll do 3 to the x equals 50. D, we'll do e to the x minus 1 equals 9. So right now, all we're doing is we're writing the logarithmic functions as exponentials, and we'll write the exponentials as logs. So you can take a second and practice this yourself. But so this is saying, the first one, saying log base 5 of 625 is 4. So my base is 5. Logs are equal to exponents, so my exponent is 4. And this equals 625. So that's all I'm looking for there. Part B, my base is 3. Logs are equal to exponents, so my exponent is 5. And this equals n. Because remember, the way that the logarithm is kind of read is, what exponent would you put on 3 for it to become n? And in this case, they're saying it's 5. Now this also demonstrates a good example of why we will want to be able to move back and forth between logs and exponentials. Sometimes we're going to need to be able to solve for a variable. 3 to the power of x equals 50. So we're putting this into log form. So I'll write log. My base here is 3. And so it's saying the exponent on 3 for it to equal 50 is x. So logs are equal to exponents, so this is equal to x. And then the 50 is in those parentheses. Now this one is nice because we can see how we get that x out of the exponent. The problem with this one is that that's actually not able to be evaluated as is. Log base 3, your calculator can't do it. If your calculator can do it, you are using an unapproved calculator. So we only allow the TI-30s, and those can only do base of 10 or base of E. And we'll learn later how we can fix something like this so that we could still solve it. Part D, my base is E, so do we use log or do we use ln whenever we see E? And we would use ln. So this is ln. If you want to write the base of E, you can. It's no biggie. Logs are equal to exponents. So this is equal to x minus 1. And my 9 goes in the parentheses. Now we don't need to write that E on there, so I'm just going to write it as ln 9 equals x minus 1. And all I was doing here was asking to move into the other form, so we won't worry about solving it any further. But if we wanted to solve this one, we would just add that 1 to the other side. Now we've kind of seen this happen, but I do want to talk about some properties with logs. If you have log base of anything of 1, that will automatically equal 0. And we saw that happen earlier in our example. When I did example C, it was a base of E and it was of 1. Anytime 1 is in those parentheses, you're basically saying what exponent would you put on A so it becomes 1? Well, that's always going to be 0. The only exception would maybe be if A itself was 1, but in that case, we would not see that because when we did the exponential section, remember I said that A had to be greater than 1, or greater than 0, but not equal to 1, is I believe what it said. Also, another property we'll see a lot is if you have log base A of A, this automatically equals 1. And as an exponential, what we're saying is the power you'd put on A for it to equal A is 1. I'm debating on whether I want to show you this one right now or not. I have it in the notes, so I'm worried that it comes up in the homework or something. I guess I'll show it to you now. And I'll remind you of it again later, I think. So another property that we see a lot is if we have log base A to the power of x, this just equals x. And we saw this one a little bit already when I did example 1F. We saw this one. But what it's really saying is, and if you write it as an exponential, the exponent you'd put on a to see a to the x would be x. And then my last property that I'll show you before we get into some other types of stuff is a to the log base of a of x is equal to just x. And if we write this as an exponential, we can kind of see, or sorry, as a logarithm, we can kind of see how it is working. So if I wrote this as an exponential, sorry, I keep saying the wrong word. If I write this as a logarithm, it's already an exponential. It has an exponent. It just has them both wrapped in, so it looks a little confusing. Think about this. I'm going to write log. My base is a. Remember that logs are equal to exponents. Well, my exponent in this case is log base a of x. And then the number by itself always ends up in those parentheses. So see how these equal each other? That's how we know that this property is true. So that one might look a little confusing to you, but if we ever see something like this, that'll just equal x. So we're kind of working our way into graphing. Before we fully get into graphing, I would like for us to practice solving for x with some exponentials. So example 3 here, I'm just going to say solve for x. So for our first one, we have y equals log base 2 of x. For b, we've got y equals log base 3, x plus 1 minus 2. And c, we have y equals 3, log base 2, x minus 1. A big reason that I want us to do this is because of how we're going to graph. So I'm just solving for x. So the only way to get x out of these parentheses is to move into an exponential form. So first I'm going to write as an exponential. So that would be, so I'm writing as exponential. So this would be 2 to the y equals x. And that's it. We've solved for x. Now let's look at my next one. This one, I can't really write as an exponential until I have that logarithm alone. So first I'm going to add 2 to both sides. Now I can write as an exponential. So I'm going to put a note here. I'm writing as an exponential. So my base is 3. Logs are equal to exponents, so y plus 2 is my exponent. And now that the log is gone, my x plus 1 is alone. To finish solving this for x, I would subtract 1 to both sides. And there we go, we've solved for x. My last one, again, I don't have the log completely by itself, and I want to get that first. So first I'm going to divide both sides by 3. So now I have y over 3 equals log base 2 x minus 1. Now I can move into an exponential. So my base is 2. Logs are equal to exponents, so my exponent is y over 3. And this is equal to x minus 1. And now I can add that 1 to the other side, so I get 2 to the y minus 3 plus 1 is equal to x. So something that I like to do when trying to graph logs, I like to turn them into an exponential. That way it's just like graphing an exponential instead of having to think about the log as much. I'll explain what I mean in a second when I write this next example. Now, the first thing that you always need whenever you are graphing any kind of function is the domain. So for example 4, we're going to start graphing. But I always want to put a note here that first, we always need to find the domain. So for our first one, we have y equals log base 2 of x. For the domain, it's that the inside of the parentheses must be greater than 0. It also can't equal 0. Now the reason for this, if you think about it, so you're saying, remember what this is saying. Let's move it into an exponential to really take a look at it. So as an exponential, this would be 2 to the y equals x. If x equaled 0, is there anything, any exponent you could put on 2 for it to become 0? The answer is no, it can't happen. What about a negative number? Is there any exponent you could put on 2 for it to equal a negative number? Again, can't happen. That's why the inside of your parentheses has to be greater than 0. So for my domain here, x has to be greater than 0, so this would be 0 to infinity. Now the other reason that I like to move into exponential form is that we can choose y values. And I follow same idea as graphing exponentials. So in this case, if you remember when we graphed exponentials, I would always say whatever makes the inside 0. So whatever makes the inside of the exponent 0, that should be your first point. So in this case, what's the y value that makes our exponent 0? It would just be 0. And then I'm plugging in to get my x. So I'd get 2 to the 0 equals 1. So my first point here is the point 1, 0. Then I usually plug one below that and one above that. So below 0 would be -1, above would be 1. And I'm just plugging in. So I get 2 to the -1, so that would give me a half. So this is the point 1/2 -1. And then if I plug in 1, I'm going to get 2. So this is the point 2, 1. So I'm going to go graph these points. Half, -1, and then 2, 1. Now, if you ever need more points, then you should plug in more points. Especially if you don't really know what the shape looks like, you should definitely plug in some more points. So let's do -2 and 2. If I plug in -2, I get 2 to the -2, which is 1/4. If I plug in 2, I get 2 squared, which is 4. So I'm going to go ahead and plot these now. So this is 1/4 -2. That's just really close there. And then I get 4, 2. So let me go plot that one. And it looks like this. So here's what my shape is looking like. You'll notice that I am not passing the x-axis. I'm sorry, the y-axis. I'm not passing through the line x equals 0. Why? It's because of this right here. I said that x had to be greater than 0. So really, I have an asymptote right here. And I brought that up earlier that we would see asymptotes again. This one is at x equals 0, meaning I cannot pass that line. There is no exponent I could plug in that would get me to 0 for my x value. So my range here, I'll go ahead and write that. My range is everywhere. I've got negatives, I've got positives, everything. So -infinity to infinity. Something that I'd like to show you at this point is I want to remind you about inverses. So if we look at the line y equals 2 to the x, so it's this line, but I'm switching the x and y, which is what we do for for inverses. We graphed this one last time, but it went through the points 0, 1, -1/2, 1, 2, -2, 1/4, 2, 4. Basically, every single point has been swapped. The x and the y have been swapped. This is the relationship between an exponential and a log. So this and this are inverses of each other. That's also why for our 2 to the power of x, our domain for that one was -infinity to infinity. We didn't have any restrictions on the domain, but my range was 0 to infinity. And remember, the domain and the range swap for inverses. So we are seeing that whole pattern happen with exponentials and logs that we did in 4.1, which is the inverse section. You can also see that if I graph this, 0, 1, -1/2, this one's even smaller, 1, 2, and then 2, 4, this is what my graph looked like for y equals 2 to the x. And you can see that it's reflecting over the line y equals x to get to our log base 2 of x. Also, we had a horizontal asymptote at y equals 0 for y equals 2 to the x. Now it's switched to x equals 0. So again, we're just seeing so many relationships happen right now. The whole relationship of an inverse is that the x's and the y's switch, and we are seeing that completely happen. If we look here to here, my x and my y is just swapped from each other, so that's why they're inverses. Now that's just stuff I wanted to show you, really, so that you can also get a better grasp of inverses and why we need them, why we use them, all that kind of stuff. And it goes really hand in hand with exponentials and logs. Now I also want to explain to you why I chose to move to an exponential to graph instead of just graphing it as a logarithm. The reason is, if you graph it strictly as a logarithm, like if you leave it in this form, you have to remember that your x's will have to be strategically picked. What I mean by that is, you see how all of these x values, they're powers of 2. So if you want to pick your x's, you can only pick powers of your base to go in the parentheses. And later, if we have like more stuff in those parentheses, like if we have a horizontal shift, it may get really difficult to pick the x values. Whereas if we move it to an exponential, we get free reign on picking y values. We don't have to think about being strategic and like only picking values that work for the base and stuff like that. We don't have to worry about that as much. So that's why I choose to do it this way. So let me go ahead and do another example, of course, and this one we'll just worry about graphing the logarithm itself. So this is f of x equals log base 1 over 3 of x. And so first we want to find our domain. We will also do the range. We'll also do the 3 points. And I'll draw my graph over here. So first I like to find my domain. So it's whatever's inside those parentheses has to be greater than 0. So in this case it's just x. So this is going to be 0 to infinity. That also lets me know that I have an asymptote at x equals 0. So I'm going to go ahead and plot that on here as well. I know I can't go past that. Now, if you would like to just choose your x values here, you're welcome to. You just have to remember that you can only pick powers of 1 over 3, or 3 in this case. My personal preference is to move to an exponential, so that's what I'm going to do. So I have y equals log base 1 over 3 of x. As an exponential, this is 1 over 3 to the power of y equals x. And now I can plug in whatever y values I want. So the rule for exponentials is whatever makes the exponent 0 is a nice point to pick. So that would be 0 in this case. 1/3 to the power of 0 is 1. So my first point is 1, 0. Now since my y is in my exponent, I like to do -1 and 1. So if I plug in -1, I get 3. So this is the point 3, -1. If I plug in 1, I just get 1/3. So this is the point 1/3, 1. Plotting some points now. So I have 1, 0. I have 3, -1. And then I have 1/3, 1. If you need more points, plug in more points, but here's what my shape looks like. So this one's kind of interesting. What we're seeing here is because that a turned into a fraction, we're actually seeing kind of a flip happen. And my range for this would be -infinity to infinity. Now again, if you would like to do yours without moving into an exponential and you want to just pick x values and like leave it with the log, that is perfectly fine. You would just only be able to pick x's that are powers of 3 because your base is 1/3. I have a preference obviously, but whatever you like. Let's do some where we start to have some more shifts and stuff like that in there. So for our next one, we're going to do y equals log base 2, and this one says x minus 1. We're going to do domain, range. We're going to find 3 points. And I'll draw my graph right here. And now we can keep transformations in mind here. That -1 is in the parentheses with the x, so we should expect that to move us to the right by 1. So something kind of to just keep in mind. Now my domain is whatever's inside the parentheses has to be greater than 0. So in this case, x will have to be greater than 1. So my domain is 1 to infinity. You'll notice that I don't put a bracket. It's because it can't actually equal that. So my vertical asymptote has shifted. It has shifted over to 1. Because that's the point that I won't be able to go past when I draw my graph. So again, if you want to pick x values right now, you can do that. You can't plug in 1 because that's not in the domain. You would have to pick x values so that when you plug it in, you get a power of 2. So you'd have to just think about it a little bit. So for instance, with this one, if I go ahead and pick x values, if I do it that way, 2 would be good, because if I plug in 2, I get log base 2 of 1, which is 0. So that's a good point. I could plug in 3. That would give me log base 2 of 2, which equals 1. Really, I find it hard to get close to the asymptote with these, like with this method, because I find that you just kind of get bigger and bigger. You don't really pick like smaller values, but it's fine. I can't plug in 4 because that would give me log base 2 of 3, which I can't simplify easily. I can plug in 5 and do log base 2. That would give me 4, which equals 2. So I can do it this way as well, and this is perfectly fine. Or you can move it into an exponential. As an exponential, this is 2 to the y equals x minus 1. So 2 to the y plus 1 equals x. And then for this one, you just treat it like an exponential. So you pick a y value and plug it in. So the first one I would pick is 0 because that makes my exponent 0. So 2 to the 0 plus 1. So that's 1 plus 1, so that's 2. So that's a good point. Let's go ahead and plug that one in. If I plug in negative 1, I get 2 to the power of negative 1 plus 1. So that's going to be 1.5. So I get 1.5 negative 1, so that's here. See, I couldn't really get that one whenever I plugged in to, like, as the logarithm. So I didn't get, oh, I'm plotting this too far over. Goodness gracious. Y'all see what I did? I was plotting too far over. Here we go. I'm not getting close to my asymptote whenever I do it the other way. Like in the yellow, when I just pick x's, I find it harder to get close to your exponent, to your asymptote. But with this method, you get pretty close. If I plug in 1, I get 2 to the 1 plus 1. So that's 2 plus 1. So that's 3. So I get 3, 1. So some of the points we ended up getting the same ones. But I mean, it really is up to you. Like whatever you feel more comfortable with is perfectly fine. So I got 2, 0, I got 1.5, negative 1, and I got 3, 1. My range is negative infinity to infinity. I can have whatever y value. Let's do a harder one. So this one, part D. That's a 3 right there. Let me rewrite it. Log base 3 of 2x minus 1 plus 1. And we'll do all the same stuff. So first I need to find my domain. So it's whatever is in the parentheses, we take it and we set it greater than 0. So this would be 2x greater than 1. So x has to be greater than 1/2. So my domain is 1/2 to infinity. This also means that my asymptote is at x equals 1/2. So I'm not going to be able to go past that. Now the inside of those parentheses is kind of complicated. So this is one of these cases where I would probably like to move into an exponential, not pick x values, because I have to remember you'd have to pick an x so that when you plug it in, the parentheses is a power of 3. I just feel like that's a lot to think about. Let's just move into an exponential. So as an exponential, first I'd move that 1 over, so I get y minus 1 equals log base 3 2x minus 1. Moving into an exponential, I get 3 to the y minus 1 equals 2x minus 1. And then I would solve it for x. So if I add 1 to the other side, and then I can divide by 2. And so this method ends up giving us a little bit more to like solve for, I guess. Like it's a little bit more work to plug it in, but I don't have to think so hard about what I can plug in. I can still just plug in whatever y value I want. So the y value that would make the exponent 0 in this case, let's think about what that would be. So what makes the exponent 0? That would be 1. So I would get 3 to the power of 0 plus 1 over 2. So this will give me 2 over 2, which is 1. So my first point here is 1, 1. Now I am already really close to that asymptote, so if you want to pick something closer to the asymptote, you could. But remember, we can't go past 1/2. So like 1/2 is like our cutoff. We cannot even plug that in. So I wouldn't plug that in or anything. I would just go bigger for this one. So let's see if I plug in 2, what do I get? So this would be 3 to the power of 1 plus 1 over 2. So 4 over 2, so 2. So I get the point 2, 2. And I can plug in something else that's bigger. So 3, so this would be 3 squared plus 1 over 2. So this gives me 10 over 2, so 5. So I get the point 5, 3 for this one. And I know that I can't go past my asymptote, so I know that my graph looks something like this. Now that was a fairly hard one. Range is still negative infinity to infinity. We were able to plug in whatever y we wanted, and we can see that the arrows go up and down. My last little subtopic here is finding the inverse. So what example number are we on? That was a bunch of graphing, but it was all under the same one. Example 5. For these, I would like us to find the inverse function. And so the way that it'll say is I'll say find f inverse x for f of x equals 1/2 times 6 to the x minus 3 is this function. So sometimes instead of saying find the inverse function, they'll just say find this, and that means the inverse. Because that's that notation stuff. So remember from our inverse section that was 4.1, we first changed my f of x to a y. Then I swap x and y. So I get x equals 1/2 times 6 to the y minus 3. And then I need to solve for y. So to solve this for y, I have this multiplied by 1/2. So I can multiply both sides by 2 to go ahead and get rid of that. So that gives me 2x equals 6 to the y minus 3. Now, much like with the logarithms that we dealt with, we moved to the exponential form to be able to get the x out of the parentheses. If you want to get something out of an exponent, you have to move to logarithmic form. So in this case, we're going to, here, I'll come up here. I'm going to change to log form. Now my base in this case is 6, so it'd be log base 6. Logs are equal to exponents, so that's equal to y minus 3. And now my 2x is in these parentheses. And to finish solving for y, I'll go ahead and add 3 to both sides. And then we finish it off with our notation for the inverse. And we're done. I'll make another one of these. We'll say find the inverse of f of x log base 2 x minus 1 plus 4. So that was the other one I did was one where we go from exponential and we're finding the inverse. So you'll find that your answer should be a log. For this one, since we're starting off with a log, our inverse is going to be an exponential. So first I change this to a y. I want to move it to exponential form so I can get that x minus 1 out of the parentheses. Can't do it yet though because I need to sorry. You can solve first, but really I should change the x and y first. Let me go ahead and do that. All right, now I'm solving for y, so I need to get y out of the parentheses. So I move the 4 over. So I get x minus 4 equals log base 2 y minus 1. Now I'm going to change to my exponential form because then I can get the y minus 1 out of the parentheses so it's not stuck in that log. So that would be 2 to the x minus 4 equals y minus 1. And then I add the 1. And I'm pretty much done. Just got to write my notation. All right. So that was it for 4.3. Kind of a lot. If you're having any trouble with exponentials and logs, please reach out to me. I'm just kind of going through for a second and seeing if there's anything I really wanted to talk about or anything like that. I don't think so. In our next section, we're going to talk about the properties of logarithms and we'll start getting more into like using them to solve equations and stuff like that. But first, we just had to talk about inverses and graphing them and what even is a log. Again, if you're still asking yourself that question, what even is a log? It's the inverse of an exponential. A lot of the time, it's used kind of for the properties you see here. You move to log to exponential form most of the time to get stuff out of the parentheses. You move from an exponential form to a logarithmic form to get things out of the exponent. That's what they're often used in junction with to do. Logs themselves are equal to exponents. So whenever you're evaluating log, you want to think about the exponent that you would need. All right. If you have any questions, as always, please let me know. I would love to help you out. And I'll see you in our next video. Bye-bye.